find that for residue, we must know Lorentz series expansion. Residue is nothing but in the Lorentz series expansion, the coefficient of this term 1 by z minus z naught is nothing but residue. The coefficient of this term, see here, the coefficient of 1 by z minus z naught. So this, what is the coefficient? A minus 1. This is called as residue. Residue means some leftover part. The meaning of residue you all know in general. No, the function if it has a pole of simple pole of order in M, then we can find the residue of function at that point. Means we can, in the Lorentz series expansion, what will be its coefficient of what will be the coefficient of term 1 by z minus z naught. Residue of f at simple pole calculation. Simple pole means how my function looks. Some phi of z by psi of z, where psi of z is equals to z minus z naught. F of z is equals to phi of z by some psi of z. In this psi of z, there will be a term z minus z naught and some extra term f of z, as we have seen in the earlier example of cos pi z divided by sin pi z into z minus a. We have seen the example of simple pole, the same thing. If it is a simple pole, my function looks like this, where denominator term will have z minus z naught, and due to this term my function will not be analytic at point z naught. So how to find the residue of the function at that point? The residue of f at z naught is equals to phi of z naught. As numerator will not have any problem and numerator value will not be equals to 0 at z naught, we are going to put z naught in the numerator, phi of z naught, and we are going to take the derivative of function psi dash of z and calculate the value of psi dash at z naught. Residue. This is just a formula you can remember. With an example, I will illustrate it very clearly. Now, residue of f, if it has a pole of order m. How to calculate it? Residue of f at z naught, if z naught is a pole of order m. Clearly we know the function looks like g of z by z minus z naught raised to m. Now we are going to take m minus 1th derivative. If it is pole of order m, we are going to take m minus 1th derivative of the numerator function g of z and put the value z is equals to z naught and calculate that, divided by m minus 1 factorial. Okay, sorry, here the term must be limit z tends to z naught. Here, this and this formulas are same, only a notation difference. Here also we are going to take m minus 1th derivative, and however this term will be there, so it gets cancelled, and we are going to take m minus 1th derivative of whatever remained in the function f of z, that is g of z. Now, residue at infinity is calculated as minus of sum of all residues of f at its finite poles. Okay, residue at infinity is minus sum of all residues of f at its finite poles. With an example, we'll see here. Find the residues of the following functions at their poles. Now, poles, simple pole or pole of order n. It depends upon the function. Now, first function is 1 by z minus 1, and the z minus 1's degree is 1, and as z is equals to 1, it has a, clearly by seeing it we can understand it has a singularity, simple pole. Okay, at z equals to 1. Now how to calculate? How it looks? Phi of z by psi of z. Here the numerator is 1, means our phi of z is 1, and denominator psi of z is z minus 1. Sorry, here it is, we have a mistake. It should be phi of z naught, not 0. Now residue is, formula is phi of z naught by psi dash of z naught. Z naught is 1, phi of 1 by psi dash of 1. phi of z is 1. Phi of 1 will be 1. It is a constant. And psi dash, derivative of z minus 1 is 1 because derivative of z is 1 and derivative of 1 is 0. So derivative is 1. So this will be 1 by 1. So residue of f at 1 is 1. Since see, psi dash of z is 1, psi dash of 1 is also 1. Next example. How this function is f of z is equals to z square minus 1 by z plus 3 into 3z. Now here, how to check whether the function has pole, be a pole or removable. Actually, how to find the singularities? First of all, if my function is some g of z by f of z or whatever, it is in quotient form where the denominator becomes 0, that point will be singularity. So here, when the denominator becomes 0, see, you can equate it and see. 3 is constant. If z is there, if I put 0, some function divided by 0 means 1 by 0 means denominator is 0, it is infinity. Now z plus 3, if I put minus 3, this becomes 0. So at which points I have problem? Z equals to 0 and z equals to minus 3 means at these 2 points function is not analytic. And what is degree of this 1 and what is degree of this 1? So these two are the simple poles. How many poles are there for this function? There are 2 poles and both are simple poles. We are going to calculate the residue of function at 0 first. While calculating the residue of function at 0, due to which term my function becomes not analytic? Due to only 3z, no? See, if I put 0 here, 0 minus 1, minus 1, 0 plus 3, 3, so minus 1 by 3, and only the term which makes the function denominator 0, that will take as psi of z, and rest all will take in the numerator, z square minus 1 by z plus 3. So if I put 0 here, this function has no problem because of psi of z is equals to 3z. This function will create a problem in the denominator. Means while finding the residue of f at 0, what is my phi? This term, only this complete term, and psi is 3z. Okay, psi of z is 3z. How to calculate residue of f at 0 is phi of 0 by psi dash of 0. Now, phi of 0 is minus 1 by 3. Here if you put 0, minus 1, 0, 3. So minus 1 by 3. And what is derivative of this? 3z's derivative is 3. Okay. And psi dash of 0, again 3 only. 3 is a constant. So residue is minus 1 by 3 divided by 3. That is minus 1 by 9. Now while calculating the residue of f at minus 3, what will be our phi and psi? Now we will have a change in phi and psi. Which function makes problem in the denominator? This, no, z plus 3, while calculating the residue of f at minus 3. But this, if I consider z square minus 1 by 3z as phi, sorry, where it is? Yeah, here. If I put here minus 3, no problem. Means only this term is creating a problem. So this will consider as phi, this will consider as, so this will consider as psi, this will consider as phi. Now we'll calculate. Wait a minute. Residue of f at minus 3, phi of minus 3 by psi dash of minus 3. Phi is what? Phi is z square minus 1 by 3z. Put here minus 3 square is 9 minus 1 divided by 3 into minus 3 minus 9. That is minus 8 by 9. Here psi dash of minus 3 is 1 because psi dash is derivative of this. Psi of z is z plus 3, psi dash of z is 1. Constant term psi dash of minus 3 also 1. what you get, residue of f is minus 8 by 9 by 1, it is minus 8 by 9. Now the third example, f of z is equals to cos z by z cube. If I put z is equals to 0, denominator becomes 0. And what is the degree of this term? 3. Means z is equals to 0 is a pole of order 3. Now how to calculate? Now here it looks like some g of z by z minus z naught raised to n, as we have seen in the definition of pole. So what will be our g of z? Cos z, and it is pole of order 3. So how many times you are going to take derivative? 2 times. If it is pole of order m, we are going to differentiate is m minus 1 times. So how many times? Here the pole is order is 3. We are going to differentiate it 2 times. G of z is cos z, numerator term, and cos 0 is not 0. G of z, g dash of z minus sin z, g double dash minus cos z. Now, value of this derivative at which point? At pole. Pole is 0. So, g double dash of 0 is minus cos 0, minus cos 0 is minus 1. So, residue of f at 0 will be second double 2 times derivative of g at that point divided by 2 factorial, because 3 minus 1 is 2 factorial. So minus 1 by 2, that is minus 1 by 2 factorial, it is minus 1 by 2. Now here are some examples, you can practice it, and you this much for today. Thank you.